Share the screen. Okay. Okay. Right. So welcome everybody. We are ready to go. We are investigating localizations of rings and modules. And today we would like to investigate what happens with ideals on the localization. Especially we are interested in prime ideals. Okay. So I can start a new section. 3.4. It's extended and contracted ideals in localizations. Extended, contracted ideals in localizations. Okay. So by the way, this morning I was at FU and gave a little talk in private at the blackboard. It was fantastic. I really love to do that. Much better than Zoom. Okay, so what do we do? So I have my commutative ring, a multiplicatively closed set S. I form the localization, and then I have this canonical map F, which sends A to A divided by 1. Okay. So we have a ring homomorphism, and we would like to know what happens with extension and contraction. So let me recall these notions from the very beginning of the lecture. We have the notion of an extension of an ideal, extension of ideal A of A. Okay, we denoted it with just with the exponent E for extension. And what it is this is the ideal generated by A in S to the minus 1A, and we denote it this way. It's a suggestive notation. And then we have the contraction. Let's say of an ideal B of this other ring. So what happens if you contract? This is just by definition the inverse image. This is the contraction, right? So these are general notions, and the question is, can we describe them more concretely in the case of localizations? Okay, so I think my internet connection is again a little bit unstable. Can you hear me well? I get these warnings. It's okay?
It's fine until now.
Until now, okay, because when I get this warning, I'm always a bit worried. Okay, so when we started this lecture, there was a proposition 117 in Atiyah MacDonald, if you remember. Okay, it holds in fullest generality. Let me recall it. So let's say C is the set of contracted ideals of A, contracted ideals in A, okay, or contraction, not contraction ideal, I should say contraction or contracted, it's okay. Those ideals that you can obtain by a contraction, and E is the set of extended ideals. Here. Okay. And right, and then we had the following description, C. So this consists, the contracted ideals are those with the following property. You have taken an ideal A, you extend it, and then you contract it. So I don't put parentheses. First I extend it, and then I contract it. Certainly I get an ideal which contains A, but if I exactly get back A, then this means this was a contraction ideal. Similarly, I can denote the set of extended ideals by the set of B with the property first contract, then extend, I get extend. Okay, so this we had, and we have bijections between these sets, have bijections. Okay, they are inverse to each other. On the one hand, set of contracted ideals, on the other hand, set of extended ideals, and then it goes in both ways. Here extend, and here you have contract. Okay, so I think the general situation, it may look confusing, but if you see it this way, I think it's pretty clear what's going on. So what one has to do, one has to determine the sets C and E. Okay, once you understand what is C and E, then you know what's going on. Okay, so in the case of localization, actually we can say a lot. So now let me break up the next result into different claims. So we work it down by pieces. First claim is that every ideal in S to the minus 1a is a extended ideal. Okay, every ideal B in this ring is an extension ideal. Okay, so let me prove that. That's very simple. Okay, we can show. So we use these general principles and we show B contracted extended equals B. Okay, then I have done this, then I'm done. So and what is clear is always this inclusion. This is always true. And we have to show equality. Okay, so let's take a general element in the ring B that's of the form X over S. Okay, so right, so then what do I do? X over 1 I can write as the product S right, over 1 times X over S. Okay, so that's also in B, of course. Okay, because I have an ideal. So what I see that X is in B contracted, because remember the map sends X to X over 1. Now X over 1 is in B. So X is in the inverse image. So it's in B contracted. Okay, so therefore X divided by S is in B contracted extended. Okay, so I've B contracted. Well, if you go to the extension idea, you allow multiplication with any elements of S to the minus 1a. So you can multiply with 1 over S. So, right. So I'm done. So showed E is here. And therefore equality. You see, it's a rather trivial argument, like all these arguments. Okay, then I have a claim 2, which is a little bit technical. I can't help it. So the claim 2, no, claim 2 is not that bad. It's just an intermediate step. Okay, let's first do this claim 2 before I describe the contraction ideals. So for an ideal A of A. So I'm wondering now what happens for which ideal when I extend, do I get everything? Okay. So you understand, it's kind of, you have an ideal, you extend. If you get the ideal generated by 1, you kind of lose all information. In a way, it's, it's kind of gone. Okay. So when does this happen? Okay. Right. So I claim this happens if and only if A does intersect the set S. If and only if. And let me prove it. Okay, let's do this direction. So let's go from right to left. So remember what happens if I do localize, all of the elements of S become units. So if A intersects S, then A will contain a unit after localization. But then, of course, A extended is the whole thing, okay, because it contains a unit, right? So I think this is, let me write clear, hopefully clear. Let's do the other direction. Okay, I'm always very careful here. So let's assume, okay, the one in the extension ring is 1/1. So let's assume this 1/1 can be written in the form x over s with some element x in the ideal A and s is in capital S. Okay, so this means this. Okay, good. Now I just have to multiply. So what does this equality mean in back in the ring A? So this means, if you remember, there is some t in S such that t times x minus s equals 0. So you remember that this is this injectivity of the map F, right? Okay, so but then if I have this, then I see Tx is T mal S is T times S. And this is, okay, maybe I don't write it this way. I just Tx. On the one hand, it's in A. On the other hand is T times S, so it's in S. So I have shown A intersected with S is non-empty. Okay, so this was the claim 2. Also not much happening. Okay. Okay. So are other questions on that? Okay, now this claim 3 is a little bit more technical. So I have a little bit myself troubles to remember what this actually means or to remember it. So, okay, an ideal A of A is a contraction ideal if. So if and only if, so 2F, if and only if. Now, condition, let me write the condition. It looks a bit complicated. Fortunately, when we deal with prime ideal, it's much, much simpler. So, but for the moment, let's do it in generality. Let me write the condition. For all S in S and for all X in the ring A, the following implication holds. So if Sx is in A, then X is in A. That's a bit complicated, right? Okay. So let me prove this. I mean, yeah, let me prove this. Okay, and I claim, I can rephrase this. I claim it's sufficient to show the following. So this star condition, I claim, is actually equivalent to this. A extended, contracted, I claim can be written as the union over all S in S. And here I take the quotient ideal A divided by S. So let's see. So there are two things to do. On the one thing, we have to convince ourselves that, well, this is true. On the other hand, it's sufficient to show, right? We have to see that what I claim here is star is equivalent to that. Okay, what do we do first? Let me think. Maybe first is sufficient. So, right. Okay, let me first explain the sufficient because I'm pretty sure that this can be confusing. Let's talk about the sufficient. Right. So okay. So a contraction ideal, okay, let me a contraction ideal by definition, okay, means, or not by yeah, okay, by our characterization, maybe not definition, it means A equals A extended contracted. Okay, that's what it means. Okay, now Okay. Now, if we assume this, okay, so then we can rewrite this. So actually, what do we need to write? Okay, in this equality here, there's always a trivial and a non-trivial direction. So let me actually write it this way. Because the other inclusion is always true, is the trivial one. Okay, and so what does this mean? So, okay, how do I explain it? Right. Okay, now how do I explain that? I want to say, okay, I want to, let me clarify what I want to say. I want to say, okay, show, okay, claim, okay, I want to show this is true if and only if star holds. Okay. So now you have to see. I have to see what does it mean. I take, okay, I see, I'm not explaining it very well. What does it mean to have an element X in extended contracted? So I think it means that X over 1 is in A extended. Okay. And this means there is some S in S such that let me see. Okay, X is A contracted. I think this means this. So, right, and X, right. Sorry, X is in. Okay, this means, sorry, maybe I should have, the notation is really bad. Okay, let me, sorry. I will fix in a moment what I want to say. Sorry, this is not very clever what I'm doing here. Okay. 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 So what I claim is this. What I claim is this. Right. So why is that? Okay, so let's try, okay? X in E contracted, it means yes, I'm myself confused. I'm always confused about this point. Yeah, but exactly what it is, if you think about it. Right. Maybe I'll leave it like that. This condition, what I wrote down anyway, this is the condition S. I think I leave it to you to check it in detail that it is true. And let me continue. It is true, yeah. And let me show this. Okay, let me show that. Okay, now check this. Okay, let's go slowly. So what is that? First, the extension ideal, I denote this way and this contracted. So this means now I do every little step. I hope it will be clear. So this means x over 1 is here. Okay. So this means there is some S in S. And there is some A in the ideal such that x over 1 is A over S. Okay. Now, okay, this is all a bit of kind of a mess. Now this means there is a T in S. Now I copy what I had before. And this condition here, I rewrite as before as T times Sx minus A equals 0. Okay, good. Now, if you look at it, you see instead of TS, you can also say S. I mean, you can simplify this. It's enough to say this is the case if and only if there is an S in capital S and there is such that Sx is in the ideal A. Okay, you don't confuse the small a with this ideal A. Okay. And once we have this, then we see this is indeed the same as saying X is the union over S in S. And this condition I can rewrite. Now I can say this, okay, I put here these quotient ideals. Because the elements in A divided S are those elements X with the property that Sx is in the ideal A. Okay, so this is... right, so this is the proof of this. It's maybe not too illuminating, I agree. Right, but that's what it is. Okay, maybe we don't even have to remember it because this is a kind of a messy thing, but let's go to the next claim, which is something which is much easier and which we should remember. This is the claim 4, and this only talks about prime ideals. So when is a prime ideal a contraction? A prime ideal P of A is a contraction ideal if and only if, very nice, P intersected with S is empty. So this, okay, so this is important. Okay, prime ideal. Let's prove that, okay? Actually, maybe I shouldn't have done this claim 3 and proven claim 4 directly, but anyway, we apply claim 3. I give another proof of claim 4 later. So let's assume, so one direction is a trivial one. When P intersects S, then after extending, you get everything and it will not be right. You cannot have a prime ideal. So, so let's assume P intersected with S is empty. Okay, so then what happens? So, so what I want to do, I want to check this condition. So this terrible condition. Okay, and now I check this condition. Okay, I check this implication. Sx in P implies X in P, but this is very easy. So if I have X, sorry, I have Sx in P. Right. Now I use P as a prime ideal. So this implies either X is in P or S in P, but this is impossible because the capital S, yeah, since the capital S that we use here is just the complement of P. Okay, this is impossible. Oh, sorry, yeah, this is our assumption. Sorry, I'm confused today. This is impossible because we assume here, we assume they are, here is it? We assume they are disjoint. Okay. So I see P is a contraction ideal. Okay, I use the claim 3. And conversely, let's also say that more clearly. So if, because before it was not very clear, if P intersects S, then if I go to the extension ideal, I get everything. Okay, this is say by claim 2. Okay, so then if I go on, P extended, contracted, if I contract the one ideal, it will be 1. And this cannot be P because P is prime. So P is not contraction ideal. P not. Okay, because, yeah. Okay, so this is the claim. And so let me, sorry about the confusing claim 3. Okay, but let me summarize what is important here. So what is very important is this. At TM McDonald's, it's proposition 311. Okay, part 4, you see, I really want to emphasize this. It's about the description of the prime ideals in the localization. Okay, the prime ideals of this localization ring, okay, are in bijective correspondence with the prime ideals of A that do not meet S. Do not meet S. Okay, very important. Okay, so I have shown this. Okay, so let's illustrate this. Let's illustrate this a little bit. So there is one special case of localization that occurs very often. This is localization with respect to a prime ideal, right? So you have a prime ideal, and the set S is then the complement of the prime ideal. And the localization that you get in that situation is a local ring. Okay, so let's phrase this as corollary 313. Let P be a prime ideal of A. Okay, then the prime ideals, and I will have a picture in a second, the prime ideals of the local ring, so A localized P, are in bijective correspondence okay, with the prime ideals of A, well satisfying what? Prime ideals of A. Okay, and what is the property? Now I ask you, what will it be? Let's see whether you are confused or not. Those prime ideals, they do not meet the S. The S is the complement of P. So this means those prime ideals that are contained in P. Contained in P. So and the proof, okay, yeah. The proof is just apply the proposition to the case where S is A minus P. That's the proof. So I know questions or not so. Let me draw a picture. Maybe a picture helps. Okay, kind of. Okay. This is my ring. Okay, so now it's a cartoon. This is my ring. And then let's say, okay, this object here, maybe I can put it in color. This object, this set. Okay, this is the prime ideal P. Why not? Okay, so this is the whole thing. This is P. Okay. So now what I will do, okay, inside here, maybe I have another, okay, I have a Q. It's another prime ideal. Okay. Now, what happens when I localize? Okay, then when I localize, certain information disappears. So let me here, this is now AP, cartoon of the local ring. The local ring has exactly one maximal ideal. And this is the ideal, which is the extension of P. So here, maybe I also do it in yellow. So this thing, it's like, okay, this yellow thing. This will be the extension of E. And this is the maximal ideal of the localization. Okay. And so the orange guy, I mean, if I extend it, it is contained here. So maybe this is the Q extended. All right. And I have a bijection. Okay, the ejection is not on the level of ring, but it's on the level of prime ideals. I have a bijection between the prime ideals contained here in P and the prime ideals contained in P extended. Right. You see, but I may also have other, I may have a prime ideal which lies like that, okay? Right, that's possible. But those prime ideals I don't see anymore after localizing, okay? If you have a prime ideal that has an element outside of P, so meaning an element in S, if I localize, it disappears. So it becomes everything like not visible anymore. Okay, so I hope this picture helps a little bit to visualize what's going on, right? Okay. So, and this can be, I mean, this picture is almost geometric. And actually, it helps to think a little bit geometric here. I don't have much time to go into it, but let me, okay, at least explain the very first beginning. So let's reformulate it, reformulation. Okay, we write. So now we introduce a name for the set of prime ideals. Let's call it the spectrum. The spectrum of the ring A. Sometimes people do parentheses. This is the definition. It's just a set of prime ideals of A. Prime ideal of A. Okay, so this is the spectrum. Spec. So now, so this comes with it. Actually, one gets a functor. So then the map from F, the ring homomorphism, to a localization, let's say AP, this induces the, okay, a pullback map. It goes in the other direction. It goes from the spectrum of AP to the spectrum of A. Now it looks kind of bit complicated, but what's going on? I have to a prime ideal Q of A, I have to assign a prime ideal in the localization. And what do I do? Let me see. I do the extension ID. Now, sorry. What do I do? Right. Yeah, I do the contraction, so this is okay. Yeah, I have a prime ideal here. I take the inverse image, the contraction, that's a prime ideal. So this F star is a well-defined map. Okay, so I have this map. Okay, you clearly see that I can have this F star for any map. I mean, here I could have any ring homomorphism from A to B. I would get the corresponding map from the spectrum of B to the spectrum of A, exactly doing that. Okay. But here we can say more. So we can say that this map F star here, also F star is injective. With image. Okay, so what is the image? So let's write image. Now image of the spec AP. Okay, so we know what this is. The image, these are those prime ideals that are contraction ideals. Okay, but we know these are exactly by this corollary 313, by this, these are exactly the prime ideals contained in P. Okay. So what I'm trying to do here, this may be confusing if you see it for the first time. It takes time to get used to it. So in a way, I invent some kind of geometric language, okay, to describe what's going on here. Right. Question on that? Somehow I feel I didn't explain it too well. I don't know. So maybe there are questions. So why is it injective, the map? I didn't say why is it injective. So suppose I give you Q contracted. How can you reconstruct Q?
By extending.
Just by extending, correct. By extending, yeah, just by extending. Okay, so, but this picture that I have here, it's quite important. So, you see, I have my ring A. Inside, I have the prime ideal. And now I have a way to look only at the collection of prime ideals contained in P by going to the localization. But there is like an alternative viewpoint. There's also an algebraic way to look at the collection of prime ideals that are containing P. So like these guys, okay, I can also do that by going to the quotient ring. Let's also explain this. We know that already, but it's just to complete the picture. So by contrast. Okay, so I have the canonical ring morphism from A to A mod P, let's call it pi. This induces, okay, a pi star going from the spectrum of A mod P to the spectrum of A. So what do? I always go to the inverse image. Okay, primes go to primes. So I have this map. And this map is also injective. Injective as well with image. Okay, what is the image? So this looks all a bit fancy, but in a way it's extremely simple what I'm doing. So the image is which prime ideals? Okay, so which, the question is which prime ideals here can I get? Yeah, this way. So which prime ideals in A arise as inverse image of a prime ideal here?
That contain the ideal.
Sorry, can you say again? I didn't hear.
That contain the ideal.
Right. So P has to be, sorry, P has to be, that's right, that's all. It would also be true when I don't say prime, okay? Because the ideals that I obtain as inverse images of the ideals here are just the ideals containing P. Okay, so kind of I factor out P. Okay. So now we see we have kind of two constructions. I have my ring A and I have a prime ideal P. I can on the one hand form this factor ring, look at the spectrum of it, or I can form the localization. Okay, and it has very different effects, kind of complementary effects. Okay, but in both situations, I kind of make the spectrum smaller. Okay, I kick out certain prime ideas. So these both methods are very common techniques. So if in commutative algebra, you start to prove theorems by induction and so, then these are important techniques. We will see that. Okay. Right. So okay, I want to, okay, I have another thing that I want to explain. The localization. I think I already proved localization commutes with taking tensor products, but it also commutes with taking quotient rings. So this is also a nice observation. One should make it. So let me explain it. Localization commutes with taking quotient rings. Okay. So what is the setting? So my script A, this is an ideal of the ring A. I have a multiplicatively closed set. Okay. So then let's see, what can we do? Here is A. I draw a commutative diagram. So I can form the quotient. It's the factoring. I denoted A bar. Okay, I do this. Okay, quotient out A. Right. I can also, on the other hand, I can form the localization. It also comes with a map. This is vertical map. But I could also localize this guy, the A bar. Okay, with respect to what? Well, for the multiplicatively closed set, I just take the image. So let's denote S bar. Okay, it's maybe an intuitive notation is this, but this is formally defined as pi of S. S bar is just pi of S. It's a multiplicatively closed set. So I can form here the localization. S bar to the -1 A bar. This is defined. Okay. So you see, first factoring, then localize. Here, first localize. And now let's see, what is this map? Is there a map? And the point is yes. Okay, there is a map. It exists. So my point title exists. I claim by the universal property of localization. So what was this universal property? Right. We need. Okay. If I compose these two maps, I get this diagonal map. Okay. And I need to know that this diagonal map maps elements of S to units. But this is what happens. If you have an element of S, it goes to S bar and will be a unit. So clearly, I can factor. Okay. So this map Y twiddle exists. It's a ring. I say map, but I mean, of course, ring homomorphism. Okay, and then now very easy to check what is the kernel. What is the kernel of this guy? Well, this you check yourself. It's just the extension. So the pi sends A to 0, and the pi twiddle sends the extension ID of A to 0. Very easy to check. So what we obtain here, so we see this here gives me the quotient of this ring by this ideal. Okay, so I can write it this way. So we obtain, but you see the best way probably to see this via the commutative diagram. So I have this divided by this idea, but this is isomorphic, actually canonical isomorphic to that. Okay, and I can write this. It's a bit ugly, but I can still write it. No, it looks ugly, but that's what it is. Okay, so this shows that taking localization and taking ring quotients, they commute. It doesn't matter in which order you do it. Nothing can go wrong in principle, right? Okay, so this proof I gave, so I'm a bit bad conscience. This claim 4, what this was claim 4, a prime ideal of A is a contraction ideal if and only it doesn't meet S. I proved it using claim 3, but I messed up claim 3. So let me redo the proof of claim 4. Hopefully I can make up, and it will be clearer. So I want to use this observation, which is now in the orange box, to directly verify the following. Okay, let's use this. Let's use this to directly verify this implication. So prime ideal, P prime, ideal of A, P doesn't meet S, then the extension is prime. Stays prime ideal. Okay, so I want to reprove this. I want to give a different proof. Okay. So you see, I mean, the way I remember this, P intersected S empty, P doesn't meet S. So this means that the extension ID will not be everything. Okay, but it is not a priori clear that it will be a prime ideal, that this property of being prime is preserved. Okay, I proved. Now let's give this direct proof. So this is it's quite neat. So look. So one way to characterize prime ideals is to go to the quotient ring, A mod P. I call it A bar, and this is an integral domain. Okay, so I want to prove somehow preservation of integrality. Okay, so I want to localize this guy with respect to, okay, I write it here. So I have S bar. Right, I have my set S, I go to S bar. Okay, but I have to make sure, you know, when in the localization, when in this, generally, when in the S that ends up a 0, then the localization collapses, you get the 0 ring. So I don't want to have this. And this I don't have since P intersected S is empty. So P intersected S empty, okay. This exactly means this. Okay, so what I do now, right? So now I use this orange thing, and then I see so the localization. Okay, let me write it. So I claim this localization is a subring of the quotient field of A bar. So I have A bar, it's an integral domain. So in a way, the maximal localization is the quotient field, okay? This is the biggest possible S that you take, okay? All non-zero elements. That's the quotient field, right? So, but now I just localize with respect to S bar, okay? They get something a little bit smaller, okay? Good, I have this. Right, and it's not zero. I just said it's not zero because of that. Okay, it's not zero. So therefore, this subring is an integral domain. Okay. Okay, integral domain. The quotient field is an integral domain. Every subring of it is an integral domain unless it's zero. Okay. So therefore, now now comes the orange box. This is the same as this. Okay, so now I see I have shown this is an integral domain. So therefore, this ideal must be a prime ideal. Okay, and I have proof. This is yet another proof, conceptual proof, basically calculation-free proof of this property. So maybe let's put it in orange. Right, so calculation-free argument for this important implication. Questions?
Yes, a question. So S bar is in, I mean, usually when we use this quotient notation, we would assume that P is contained in S, but now it should mean just the corresponding equivalence classes that
Yes.
have representatives in S.
Right, so pi is this. This is the canonical morphism. And S bar, I define as pi of S, as I did before, okay?
Ah, okay.
It's just, this is the same as I did in this more general context. Yeah. Okay, so you see, in a way, the way I see it, you can only learn this by using it. These by itself, these are not like great results. These are techniques. These are just techniques. I mean, you learn it by doing. You use it, okay, and then you learn it, and then you see it's useful. These are methods, okay, ways of. Okay, so one last word about this localization is, but I don't even want to prove it. But the proof is very simple. It says localization is so nice. So in Actia McDonald's proposition 3.11.5, so he packed everything into one proposition. So I kind of unfolded it to explain it better. So this says that look, the operation of localization commutes with taking finite sums, finite products, finite intersection, and so on. So it's, let me write it. Okay, consider operation. Okay, what is the operation? Ideal A of A map to this extension ideal of the localization. Okay, so this operation commutes with the following things: finite sums. So you may take here like a sum of two ideals, then localize, or you can first localize and then take the sum. It's the same. Or what do I have? Finite products. Or you can do finite intersections. Or you can compute radicals. That's all true. And the proof is very elementary. Okay, and I wanted to state it. Right. So you shouldn't be afraid of localization. The definition is abstract, but you see all the proofs are very elementary and it has all these wonderful properties. Okay. And this is the algebraic way of having a local view. Okay. Instead of, I don't know, you have something, a big thing. You have like, I don't know, a surface. I don't know. But then you say, here is this little point, and I just look locally what is around. Geometrically makes a lot of sense. In geometry, you would do this all the time. You just look locally. And that's, I mean, if you do this in an algebraic setting, algebraic geometry is exactly the method. You localize. That's what you do. Okay. Maybe you believe me, maybe not, I don't know, but that's it. Okay, so my plan is, I have to make up time because I spend a lot of time on the Grübner basis. So I will now jump directly to the next chapter. So there is, in Atiyah MacDonald, there are some things that are extremely useful, but it's only in the exercises. So one could have a discussion of the spectrum of a ring. I mean, I just make the definition, but one could define it more closely. One could define the Zariski topology, and one could see what is the behavior on the maps, etc. So all of these things, which are exercises in Atiyah MacDonald, I just skip. Okay, these are exercises, but very important exercises. So I will jump over it. So maybe we can have some things in the exercises and move to the next chapter. Okay, so let's go. End of localization. Let's start a new topic. But not end of localization. We'll use it. We use it, of course, in the proofs, but it will not be applied. So chapter 4 is integral dependence. Okay, integral dependence. Actually, in Atiyah MacDonald, it says n valuations, but I will skip valuations. It will be just integral dependence. Okay, integral dependence. So let me write. So okay, section 1 is also integral dependence. Why not? Okay, so what is that? Right. So you know from algebra 1 the notion of an algebraic field extension, okay? Which leads to the Galois theory. And what we want to do, we want to study a related concept, but where there are no fields, just rings, okay? But otherwise, it's the same concept and it's very important. And this is integral dependence. So, okay, let's assume I have an extension of rings. A is a subring of B. A, B, B a subring. I have a ring B with a subring A. So now I want to define what it means for an element of B to be integral algebraic over A. So I have an element X of B. Okay, this is called integral. Okay, if you want to be very detailed, you say integral algebraic, but people usually just say integral if, let me underline this, integral algebraic over A. So algebraic would mean for fields, there is a polynomial with coefficients in A, which has x as 0. Okay. Now I would write the same. So where is the subtle difference? Over fields, I mean, you may always assume that your polynomial is monic, in German normiert. So the leading coefficient is 1. And if it's not monic, you just scale it and it will be monic. So this is something you cannot do over any rings because your leading coefficient may not be a unit. Solution is you just require it. Okay. So if X satisfies a monic polynomial equation. Okay, let's write it. Let's put a star. So x to the n, you see the coefficient is 1 plus a1 x to the m minus 1 plus plus an equals 0. ai is in a and greater or equal to 1 with coefficient. Yeah, I can, okay, if I want to have it in text with coefficients in a, it's already in the formula. Okay, so that's integral, definition integral. Okay, so remark. A couple of properties. So it's obvious an element A in A is integral over A. Okay, the equation is just x minus A. It has a 0 A. It's monic. The coefficients are in A, right? Good. So now let's make very clear the connection to field extensions. Suppose A in B is a field extension. And X is in B. Okay, then, okay, I say algebraic and integral is just the same. So X is integral over A. I drop this algebraic because it's, it's too long. If and only if X is algebraic over A. Okay. Maybe let me write why, because it's an important point. So this direction is clear, and the other direction is divide by leading coefficients. Okay. Okay. Good. Any questions? Examples? Let's do some examples. So let's say A is the integers, B is the rationals. Okay, let's check. Okay, let's take a fraction. X is R over S. It's a fraction. So when is this integral over the integers? Okay, integral. Let's see, what are the options? Okay, so let's assume, I can assume that the GCD of R and S equals 1. So this is in German gekürzt. Okay, I clear denominators. So then write, if it's integral, then this, let's put the equation star. Okay, so this is this equation. I just, instead of x, I write r over s, and then I multiply with s to the n. Okay, so I will know no fractions anymore. Then I have r to the n plus a1 r to the n minus 1s plus blah, blah, blah. I get that. Okay. Good. And right, now you see the s. S appears as a summoned in all the terms except here. So what I have here is a multiple of s. So I see s divides r to the n. Okay. But since I assume s and r are coprime, so what do I? Okay. So since they are coprime, the only way this can happen is s is plus or minus 1. Okay, they are coprime. Okay, so I see x actually is an integer. So what I have shown is, yeah. Okay, let me summarize what I have shown. And actually, if you look at the proof, it works in more generality. So by the same reasoning. Okay, A is a factorial ring. Before it was the integers, but the argument works for any factorial ring. B is the field of fractions of A. Okay, then the only elements of B that are integral over A are the elements of A. B is in B integral over A implies X is in A. Okay, the other implication is also true, but this is trivial. Okay. Okay, back to the fractions. A fraction is integral if and only if it's not a fraction. Okay, but there are some rings that are not factorial. I mean, they are a bit strange and so, and then you don't have this. Okay, but this is the nice situation. Okay, good. So what are good theorems about? I ask you now. It's so quiet today. You know, algebraic extensions. What do you know about algebraic extensions? So what should I, what should I prove? I mean, what should I try to extend? Algebraic extensions of fields. What is an important? No, it was important.
Tower law.
Can you louder?
Maybe the tower law.
Oh, tower law. What is tower law? Yeah, maybe say what is. It sounds good, but what is it?
It has to do with some kind of degree of extensions.
Right. Good. This is even quantitative. Right. So I have a field extension, an algebraic one, and another one, like 2. Okay. Okay. Then altogether, it's also algebraic. Right. Moreover, you can measure like the size of the extension by a notion of degree. That's what you want to say, right? It's the vector space dimension. And then it is multiplicative. Very good, correct. I want to do the same, but I'm a little bit more modest. Why? When you define the degree of a field extension, say you go from K to L, the point is you can view L as a K vector space, and then you talk about dimension. Now I have these arbitrary rings. It's not so clear what would be the notion of dimension in general. So maybe I don't do this here. So in a way, so I will prove this power law, but without, not quantitative. Okay. I want to show transitivity. You have an integral extension. Okay. But before doing so, I should define what is integral extension. Okay. So let's go, right. So let's go step by step. Right. So there is one auxiliary result, which is extremely important here. This is the main technical method. And it's related to kind of the Nakayama lemma, characteristic polynomial, and these things. It's all the same idea. So it's really important. Let me important. Huh? So here is something happening, is important. So what assumptions? I have a ring extension, let A, B, B, ring extension. I have an element X in B. Now I want to have different criteria when is X integral over A. So equivalent are the following conditions. So maybe I move this here. Good. First condition, that's what I'm interested in. X is integral over A. Okay. But I want to have other conditions where I don't have an explicit equation that are somehow easier for proofs. Condition 2 says, okay, let's look at the ring generated over A by X. I denote it this way. So this is not, not necessarily a polynomial ring. It just stands for the ring generated by X and A. So the elements here, they are like polynomials in X with coefficients in A, but X is not a variable, okay? So this is a finally generated A module. Okay, this is condition. Or there is a third condition, right? It's of the similar flavor. Then, so you say there is a subring C of B, which is sandwiched between AX and B, and finally generated. C finally generated as an A module. So, okay, so it's like part 2, but instead of AX, any subring. And okay, the last condition, maybe that may look a little bit weird. So that looks even more general. It says there is a faithful. Do you remember this? Faithful in German means treu. I will explain. Huh? Faithful. There's a faithful AX module, which is as an A module finally generated. Finally generated. And faithful means the annihilator of the module is 0. So faithful, maybe I write. Faithful means annihilator of the module is 0, but the annihilator here. So if you have an element A, if you have a ring element that kills the whole module, then it must be 0. Okay, this is faithful. Or the corresponding representation is injective. Okay, so this at first glance maybe doesn't look so useful, but remember all of these conditions. I mean, somehow the important thing here is the finite generated. Okay, this is finally generated, this is finally generated, finally generated. Somehow this expresses something is finite dimensional in a way. If you were over field, it would be, this has this flavor. It's like the Nakayama lemma where a module has to be finally generated. Okay, this is somehow behind it. Okay, but I can prove it, I think. Okay, I have 15 minutes, no problem to do this. Let's prove it. It's not hard. So let's go from 1 to 2. So we go in the circle. So x is integral over a. So we have some relation, which I denoted star, star. Okay, here is my star. Here it is, this one. We have this. Okay, we use that. So what this is good for, you see, look at this. So if I put these terms on the other side, I see I can express x to the n as an A-linear combination of smaller powers. Okay, x to the n is an A-linear combination of x to the n minus 1, x to the n minus 2, blah, 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 x1. Okay, and then I can repeat this idea. So then I see all powers of x can be represented as A-linear combinations of the first n powers. So from star, we get for, I think when we do inductive, let me write, x to the n plus r is, okay, I first write this. X to the r, so the a are in a. Okay, and then by induction, I claim we get, so the whole ring, this is the sum of the ax to the I over all natural numbers. Actually, I only have to take the sum over the first n terms. Okay. Because I mean, detail is first, okay. Here, first you take r equals 0, then you express x to the n as a linear combination. Then once you have this, you go to xn plus 1. Right, and write it as x to the n times x. Okay, but the x to the n you can always represent, multiplied with x, and then again. Okay, so you can reduce the degree every time. Okay, then we have this. And what we see, well, it's finally generated. Okay, so we see AX generated as a module by 1x, x squared, blah, 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 up to xi minus 1. Not more. Okay, so 2 to 3. So 2 to 3, well, there's not much to do. Okay. So for C, you just take AX, and then you're done. So it's trivial otherwise. From 3 to 4. Okay, it's also, let's see. So the funny condition for, so let's say 3 holds. Now we need this faithful module. Maybe it should have a name. Let's call it M. So what can we take? Which is finally generated the same module. If we take for M, we just take C. There is no surprise. So take M equals C. Okay. So C, again, C contains AX as a subring, so I can view it as an AX module. And it's finally generated. There is this thing about faithful, but this is clear that it is faithful because I mean, it's yeah, let me, why is it faithful? Let me write. So if I would have an element y such that y times c equals 0, then you just take, when C is a ring, so it contains the 1. Okay, then you have y is 0. Okay. So now everything was easy actually. So the only direction where something is happening is from 4 to 1. Maybe let's mark it somehow in red. So here something's happening. This is the interesting part. So we have this weird condition 4. There is this faithful AX module finally generated as A module. We have to show X is integral. We have to find this linear relation among the powers of X. Okay, and this we do with Nakayama lemma. Okay, so Nakayama. Okay, use Nakayama. Nakayama lemma. Okay, so the Nakayama lemma requires a module, a finely generated module. We have the module, it's M, and we need a linear map. So let's take phi from M to M. And this is just multiplication with X. M goes to XM. It makes sense because M is an AX module. So I can multiply with X. This is defined. Okay, but the AX I forget. It's just important. I can multiply with X. This is A linear. And I know by assumption M is finally generated. Okay, so maybe I write it also. M is finally generated A module. That's the important assumption. So then the Nakayama lemma gives me a representation. There is some representation. Have some representation of the form phi to the n. You know, this is like the characteristic polynomial thing, if you remember. So, okay, I don't write the quantifiers. There is some n, and there are some coefficients in the ring A such that this holds. So this is an equation for the map. Okay, but now, right. So what is the point? The last step is, what is this map? So this map is the multiplication with this element. Okay, this is the multiplication with this map, this element. So does the map equal 0 means that this annihilates the module. Okay, the map sending M to this thing times M equals 0. But now comes the faithfulness. It says the annihilator is 0, and therefore this is 0. Okay, and I have shown my integrality. This is the integral relation. Okay. Okay. So if there anything to remember here, this is the Nakayama lemma. Somehow the finite, I say, you know, you have the information, something is finally generated, you retranslate it to a linear relation among these powers, and that's what it is. Okay. Question? Okay, right. So there is, okay, let me, before I continue, here there is something, a little lemma and so that I skipped. So let me do it here. So, okay, in Atia MacDonald, it has a numbering. So let's use this numbering. It's proposition 216. It's rather a lemma. Okay, so I have a ring extension. Okay, then I have an n is finally generated B module, finally generated B module. And B, and the ring B is finally generated as A module. So B is a ring, but it contains A as a subring. So I can view it as an A module, and I assume it's finally generated. And then, okay, if I have this, then the conclusion is N is finally generated as A module. So in a way, this is, somebody said this tower condition. This is a transitivity condition, if you want, transitivity of finally generated. Okay, and the proof. So it's a 1 or 2 liner, very simple. So let's say y1 up to yn. Maybe I should write it more carefully. This is an n. They generate n as B module. Okay, and x1, x to m generate B as A module. So the assumption tells me I have this. So how do I combine this information, this data, to get a generating system of N as A module? So what would you suggest?
Represent and plug in, so it's trivial.
Yeah, but how can I write the generators?
So generators would be just all possible multiplications. Or
Correct. So then the point is then these products xi times yj. Okay, so all of those generate N as A module. And this is very easy to check, So, okay. Right. So I think we should not go over time this way. Last time I went 10 minutes over or 12, so maybe I stop here.